lectures on design and analysis of algorithms, and we will keep on discussing the shortest path algorithms. In the last lecture, you saw the Bellman-Ford algorithm for finding shortest path from a single source to all the vertices in a directed graph. What we will discuss today is a new algorithm called Floyd-Warshall algorithm for solving all pair shortest path problem. So let's reiterate what is the problem. Suppose we are given a directed graph G where it has vertex set V and edge set E and a weight function W, which is a function from the set of edges to R. That means corresponding to every edge there is an associated weight. We assume that the graph G does not contain cycles of weight 0 or less, that is negative weighted cycle. Okay. Last time we saw that what happens if you have negative weighted cycle. There will be certain vertices which might not be reachable. Okay. I mean the shortest path reachable in the sense that of course you can reach it, but the shortest path will turn out to be minus infinity, the length of the path. Okay. Which is sum of the addition of the weights. Okay. So we saw that essentially in Bellman-Ford we have not made any assumption about not having negative weighted cycle, but Bellman-Ford at least can tell where the negative weighted cycles are. Okay. Now here we will make that assumption that G does not contain cycles of weight 0 or less. So the all pair shortest path problem asks to find the length of the shortest path between any pair of vertices in G. Now notice the graph G is a directed graph. Okay. So every edge has a direction. Now you are asking a question that okay, given you choose any pair of vertices in this graph and ask the question, what is the shortest path between them? Okay, and how do you solve that problem? So immediately it comes to mind that okay, if I use Dijkstra to find the shortest path, how about it? If the weight function is non-negative, let's say for Dijkstra, the requirement is that the weight function has to be always greater than 0. Not about having negative cycles, but all the edge weights should be also greater than equal to 0. If the edge weights is non-negative for all edges, then we can use Dijkstra single source shortest path algorithm for all vertices to solve that problem. And that will yield an order of n cube algorithm. Okay. On graphs with n vertices, so on dense graphs and with a simple implementation. So Dijkstra will be good if I know that my weights are always positive. Okay. Now if you have an arbitrary weight function where it could be negative, what we can do is we already know Bellman-Ford. Okay. What is the rule of Bellman-Ford? Bellman-Ford can find the shortest path from a given vertex or source vertex S to every other vertex in the graph. Okay. So we can say that okay, just run the Bellman-Ford algorithm for all the vertices. Okay. Now Bellman-Ford itself takes order of n cube, and now you are going to run it for all the vertices, so the complexity of the algorithm will become order of n to the power 4. Okay. Now notice that if n is large, n to the power 4 is going to be pretty large. Okay. So it's not a very effective solution. Can you do it or lesser is the question. Okay. So here comes Floyd-Warshall algorithm. So we will now investigate a new algorithm which is essentially a direct application of dynamic programming approach, okay, that solve the problem in order of n cube time for a graph with n vertices, and this is known as Floyd-Warshall algorithm. Okay, so we'll see how to apply what is the Floyd-Warshall algorithm basic principle, okay, and finally what is the algorithm. So one thing if you notice that this is going to be better than definitely order of n to the power 4. Okay, so better than our solution of applying Bellman-Ford every time. Okay. So now let's say that how do we represent our graph, a weighted graph? So how do we represent the weights, right? So we can represent the weights just like you represent the connectivity information using an adjacency matrix. Use again a similar matrix for storing the weights. So we assume that the input is represented by a weight matrix W that is defined as follows. Okay, so let's say if I take a graph, a directed graph, so I have, say, you know, 1, 2, 3, 4 vertices. Let's number them 1, 2, 3, 4. Okay, and let's put some directed edges in them. Okay, fine. Okay, and let's put certain weights on them, and let's say this weight is 3, this is 5, this is 7, this is 2, this is, let's say, -1. Fine. Okay, so if I have weights, what we do is we can create this weight matrix, which is nothing but we will create a matrix, okay, of the size exactly for every vertex 1, 2, 3, 4. There will be a column, and for every vertex there will be a row. Okay, so 4 rows, 4 columns, because there are 4 vertices. And then you will say, okay, if I is equal to j, weights are 0, so diagonal elements are all zeros. Because there is no edge between 1 to 1, there is no edge between 2 to 2, there is no edge between 3 to 3, and so on. Between 1 to 2, there is an edge. If there is an edge, okay, then you will put the weight. Rather than typically in the adjacency matrix, you will put 1. What you will do is, in this case, you will put the weight. Okay. For 1 to 3, you do have an edge, so the weight is 7. From 1 to 4, you do have an edge, so weight is 2. From 2 to 1, there is no edge, so the weight will be infinity. I cannot reach it. Okay. So the weight will be infinity. So from 2 to 1, I cannot reach. From 2 to 1, I cannot go like that. Okay. So the weight is infinity. There is no edge like that. So 2 to 3, there is an edge, weight of 5. 2 to 4, again there is nothing, so infinity. From 3 to 1, there are no edges, so that's infinity. From 3 to 2, there are none, so that's also infinity. From 3 to 4 also there is nothing, so that's also infinity. From 4 to 1, there is nothing, so that's infinity. 4 to 2, there is nothing, so that's also infinity. But between 4 to 3, there is one edge, that is -1. So this is your weight matrix W. Fine. Okay. So that's how you form your weight matrix. So if the graph has n vertices, what we will return is a distance matrix called Dij, where Dij is the length of the path from I to j. So you will return nothing but a matrix. Again, matrix is called D, okay, and this is nothing but the distance matrix. Rows are number of vertices you have. Those are columns, same number of rows. Okay, and what Dij, anything, if I take this one, so this is D12, this is D13, right? This is D11, this is D1V, right? So these are nothing but the length of the path from the shortest length of the path from I to j at the end. Okay, fine. That's the desired format we want to get our output. Fine. So what is the total length? So and that will tell, okay, what is the path length from 1 to 2, shortest path? What is the path length from 1 to 3? So when I get this matrix, I have the knowledge of all pairs shortest paths. Right? So this distance matrix tell me what is the distance between any pair of vertices. I choose what is the distance between the vertex 3 and vertex V. So I will look into D3V. Okay, fine. So now, without loss of generality, we will assume that our vertex sets are numbered from 1 to n. Right? So that's our assumption, that we number all our vertices from 1 to n. That is, that the vertices of the graphs are numbered from 1 to n, as I just said. Given a path P, so if I have a path which is starting from V1, ending at Vm, and in between I have some vertices v2, v3 and blah 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 something. Okay, so given a path P in the graph, we will call the vertices vk with index k lying between. So that's 3. Where the index k is between 2 to m minus 1. So exclude the 2 endpoints. So if you look into all the remaining points, excluding the 2 endpoints, are called intermediate vertices of that path. So what is it? Let's go over the definition once again. Given a path P, which is nothing but a sequence of vertices v1 to v2 to v3 till vn in the graph, we will call the vertices vk with index k lying between 2 to m minus 1 as the intermediate vertices of P. Okay. So now let's understand what is the basic property Floyd-Warshall algorithm exploits. So now one thing you understand is a dynamic programming approach. If it is a dynamic programming approach, remember always in a dynamic programming approach you have to come up with a recursive solution. Okay, so there will be an optimal substructure property. Okay, fine. So the key to the Floyd-Warshall algorithm is the following definition. So let me say Dijk, k is the superscript. Okay, so let's say Dijk denote the length of the shortest path from I to j such that all intermediate vertices are contained in the set 1 to k. Okay, so essentially what I am looking into is Dijk as saying that okay, I am looking into all shortest path from I to j such that all the intermediate vertices are going to be contained in the set 1 to k. Okay, so that superscript k comes there. We are calling that as Dijk. So now if you just look into certain basic observations, a shortest path does not contain any vertex twice. If I have a shortest path, I cannot have repetitions of vertices. Why? As this would imply that the path contains a cycle. If I have a repetition of vertex, I must be having a cycle somewhere, right? It's a sequence of vertices going one after another. If there is a repetition of vertex, I must have visited a vertex again, then there must have been a cycle. So why will I walk over the cycle? I will rather go directly. Okay, so that will reduce my path. So you cannot have a cycle in the shortest path. So by assumption, cycles in the graph have a positive weight. So removing the cycle would result in a shorter path, which is impossible because you are already claiming that you have a shortest path, right? So you cannot have a cycle in the shortest path. That's the first observation. Now look at the next observation. Consider a shortest path from I to j such that the intermediate vertices are from the set 1 to k. Okay, so I am going from vertex I to j, okay, and I go to some vertex, okay, fine, such that the intermediate vertices, all the intermediate vertices are from set 1 to k. So now notice, if the vertex k is not an intermediate vertex on the path P, then what is Dijk? Recall what is Dijk? Dijk is the length of the shortest path from I to j such that all the intermediate vertices are contained in 1 to k. So now if the vertex k is not on an intermediate vertex, then Dij of k must be equal to Dij of k minus 1, because anyway it's not going to pass through the vertex k. Right? So it must be passing through the remaining vertices, which is 1 to k minus 1. The other way is that if the vertex k is an intermediate vertex, if I am actually going through the vertex k, if the path is going through the vertex k, then Dijk I can represent it as Di to k, where the intermediate vertices are from 1 to k minus 1 plus dkj, that means I go, what is the distance from k to j where the intermediate vertices are from 1 to k minus 1. Fine, okay. So I have only these two cases. I look into this vertex k and I say that, okay, my path where all the intermediate vertices are from 1 to k, okay, either I am going through one of the intermediate vertices is k. If it is true, if it is not true, if it is not passing through k, then I can look into a, the index set 1 to k minus 1. So dij k will be same as dij k minus 1. Fine. Otherwise, if the vertex k is indeed an intermediate vertex, then dij k is nothing but dik k minus 1. That means remaining intermediate vertices are from 1 to k minus 1 and I am going from di to k. Followed by I am going from dk from k to j. So dkj. What are the intermediate vertices? They are lying between 1 to k minus 1 because I have utilized k. Okay. So interestingly, in either case, the subpath contains merely nodes from 1 to k minus 1. Okay. So therefore, we can conclude that dijk is what I can write it recursively as either minimum of one of the shortest path I want. Either it is dij k minus 1, that is one possibility. The other possibility is dik k minus 1 plus dkj k minus 1. Either I am passing through k or I am not passing through k. These are the two possibilities. If I am not passing through k, I will look into the distance dij k minus 1. If I am passing through k, I will look into the distance dik k minus 1 plus dkj k minus 1. Whichever gives me the minimum is my dij k. Okay, so that's the recursive framing of the, your recursive equation of the dynamic programming approach we have taken. So, if we do not use intermediate nodes, that is k is equal to 0, that means that in the very beginning, we will start with k is equal to 0. That means we are not going to pass through any intermediate nodes. Okay. So then dij0 will be nothing but the original weight matrix wij. Right? Okay. If I have an edge, then only I can go from one to the other through, none of the vertices k is 0. Fine? Okay. If there is no edge, then it will be infinite, just like your weight. Okay. If k is greater than 0, that means k is equal to 1 or 2, fine, then dij k is nothing but the recursive formula we have just given. Okay. So finally, we have an algorithm, and that's what is called a Floyd-Marshall algorithm. So what is Floyd-Marshall algorithm? First of all, you have W. W is your weight matrix. Okay. So n is the number of rows of the weight, which is nothing but how many vertices you have. And you initialize your d vector. This is the output finally you want to get. You start with k is equal to 0 and you initialize it to w. And then you say that, okay, now I will compute this value of k. So k will go from 1 to n. Okay. So for k is equal to 1 to n, what do? You compute for I is equal to 1 to n, for j is equal to 1 to n. That is, you are computing your dij matrix. Okay, that matrix you are computing. So I definitely goes from 1 to n. It's an n by n matrix. J also goes from 1 to n. So you are going, you are essentially filling up this matrix dij, and you are filling it for dijk. Okay. So for I is equal to 1 to n, for j is equal to 1 to n, dijk is nothing but minimum of dijk minus 1 or this quantity. Now notice that when k is 1, this is 0, this is 0, this is 0, which is stored in this matrix. Once you have filled it, once you have done it, so you start with d0. Then you fill, you get d1. Then you again fill using this matrix, you get d2. Using this matrix, you will get D3 and so on. Okay, till K hits, so till you go to DM, and then your algorithm stops, and finally you return your DA. That's our desired output. Of course, you can know the actual path. Only thing is you have to keep on storing. Every time you are updating this distance, you are storing from which node you are coming to that vertex. So you store the parent value. Okay. So if you store the parent value for every vertex correctly, you can always trace the path back. Okay. So now what is the time and space requirement for this algorithm? Of course, you can see there are 3 loops. All these 3 loops are going from 1 to n. And this operation is a constant time operation. It's simply 2 additions and you are finding a minimum. So the complexity of this algorithm is order of n cube. Okay. And you can find the space complexity, you can deal with this algorithm by using a single array. So you can either use single array or 2 arrays of size n square. Okay. So your space complexity will be order of n square if you use a single array. So essentially what we have given you is an algorithm to find all pair shortest path, which exploits dynamic programming approach very nicely. So we'll stop at that. Thank you.